Between every star you see tonight, there stretches a darkness so vast that light from our nearest stellar neighbour takes over 4 years to cross it. We call this emptiness the void, imagining it as pure nothingness where matter simply ends. But sensitive instruments aboard the Hubble Space Telescope and the James Webb Space Telescope reveal something startling. That silence between stars isn't empty at all. It's filled with invisible threads of dark matter, streams of cosmic radiation, and magnetic fields so immense they could swallow entire solar systems. NASA's Planck satellite mapped this hidden architecture, showing that what we perceive as empty space actually contains 5 times more matter than all the visible stars and galaxies combined. Tonight, we'll drift through this invisible ocean that surrounds us, from dark matter halos detected by gravitational lensing to the cosmic web that connects every galaxy in existence. The darkness holds more than light ever could. Close your eyes, let the quiet settle around you, and follow me into the fullness of what only appears empty. Right now, as you rest beneath the familiar darkness of night, your eyes see what humans have always seen when looking up between the stars. Nothing. Pure emptiness stretching across impossible distances. The nearest star to our Sun, Proxima Centauri, sits 25 trillion miles away. And in all that vast gulf of space, there appears to be absolutely nothing at all. For thousands of years, this seeming emptiness shaped how we understood the cosmos. Ancient philosophers debated whether space was filled with an invisible substance they called ether, or whether it was simply void, a perfect nothingness where matter ended and vacancy began. Even today, when we say outer space, we imagine it as the ultimate empty room, a cosmic vacuum where astronauts float in silence through regions so barren that not even air exists. This intuition feels so natural, so obviously correct, that questioning it seems almost absurd. After all, if space contained anything substantial, wouldn't we see it? Wouldn't telescopes reveal clouds of matter, structures, some evidence of content between the points of light we call stars? For most of human history, our instruments confirmed this impression. Early telescopes showed stars separated by what looked like perfect darkness. Even photographs from the most powerful observatories of the 20th century revealed the same pattern. Brilliant points of light scattered across a black, seemingly empty canvas. The space between stars appeared so utterly vacant that scientists calculated its density at less than 1 atom per cubic centimetre, making it a better vacuum than anything achievable in the finest laboratories on Earth. This apparent emptiness became fundamental to our understanding of the universe. We pictured galaxies as islands of matter floating in an ocean of nothingness, with the vast majority of space containing essentially nothing at all. When Einstein developed his theories of relativity, he initially assumed space was empty except for the matter and energy we could observe. Even the concept of expanding space seemed to describe empty regions growing larger, stretching the nothingness between galaxies ever thinner. But this perception, so convincing to our senses and instruments, represents one of the greatest illusions in the history of science. The apparent emptiness that surrounds every star, every planet, every grain of cosmic dust is not empty at all. It is filled with invisible structures so vast and complex that they dwarf anything we can see with our eyes. Between you and the nearest star, space teems with activity invisible to ordinary matter, threaded through with fields and forces that shape the evolution of entire galaxies. The darkness you see when you look up is not absence but presence, not vacuum but fullness, not nothing but something so strange and wonderful that we are only beginning to understand its true nature. Consider what it means that 99% of the matter in the universe cannot be seen. If you could suddenly make all invisible matter visible, the night sky would not show scattered points of light against darkness, but an intricate web of structure spanning every direction. Filaments of matter hundreds of millions of light years long would stretch from one horizon to the other, glowing with the light of hidden particles and fields. The space around every galaxy would shimmer with halos of invisible substance 5 times more massive than all the visible stars combined. Even the seemingly empty region between Earth and the Moon would reveal itself as filled with streams of particles, magnetic fields, and forms of energy we are only beginning to detect. This revelation emerged gradually through decades of careful observation and measurement. In 933, astronomer Fritz Zwicky noticed that galaxies in distant clusters were moving far too quickly for the amount of visible matter they contained. Either our understanding of gravity was completely wrong, or these galaxies were embedded in vast structures of invisible matter. When Vera Rubin studied the rotation of spiral galaxies in the 1970s, she found the same puzzling pattern. Stars at the edges of galaxies moved as if they were feeling the gravitational pull of matter that telescopes could not detect. These discoveries forced scientists to conclude that most of the universe consists of substances that emit no light, absorb no light, and interact with ordinary matter only through gravity. Today, precision measurements from space-based observatories have quantified this hidden reality with stunning accuracy. Ordinary matter, everything made of atoms, everything we can see and touch, comprises less than 5% of the total universe. The remaining 95% consists of dark matter and dark energy, substances so different from ordinary matter that they remain almost completely invisible to our most sophisticated instruments. Between the stars, this invisible majority shapes the architecture of the cosmos, guiding the formation of galaxies, directing the flow of gas and dust, and determining the ultimate fate of every structure we observe. The silence between stars is not empty silence, but the quiet presence of forces and matter beyond our ordinary perception. A hidden cosmos more vast and intricate than anything our ancestors imagined when they looked up at the scattered lights in the night sky and saw only darkness between them. The first hints of the universe's hidden architecture came from one of the most ambitious mapping projects ever undertaken, a mission to photograph the oldest light in existence. Between 2009 and 2013, NASA's Planck satellite spent 4 years in the cold depths of space measuring temperature variations in the cosmic microwave background with precision beyond anything previously achieved. This ancient radiation, released when the universe was only 380,000 years old, fills every cubic centimetre of space around us, carrying within its faint glow the blueprints for everything that would eventually form. To human senses, this background radiation appears perfectly uniform, a smooth bath of microwaves at 2.725 degrees above absolute zero. But Planck's instruments were sensitive enough to detect temperature differences as small as 100,000th of a degree, and what they revealed transformed our understanding of cosmic structure. The supposedly smooth afterglow of creation was actually mottled with tiny variations, hot spots and cool spots that traced the locations of matter concentrations in the infant universe. These temperature fluctuations, so small they would be imperceptible to any instrument less sophisticated than Planck, map the positions of structures that would grow over billions of years to become the largest formations in the cosmos. Each slightly warmer region marked a place where matter was beginning to clump together under its own gravity, while cooler areas showed where space was being stretched thin as material flowed toward the denser regions. When scientists converted Planck's temperature measurements into a map of the entire sky, they discovered that the universe possesses an intricate geometric structure that had been completely invisible to previous observations. The pattern revealed by these ancient photons resembled a vast three-dimensional web, with dense nodes connected by elongated filaments and separated by enormous empty regions called voids. This cosmic web, as astronomers named it, represents the fundamental architecture upon which all visible structures are built. Every galaxy, every star cluster, every region of space where matter congregates follows the pathways laid down by this invisible scaffolding. The filaments themselves stretch across distances that dwarf individual galaxies, spanning hundreds of millions of light-years from end to end. To put this in perspective, if our entire Milky Way galaxy were reduced to the size of a small coin, these cosmic web filaments would stretch across continents. ESA's analysis of the Planck data revealed that these structures contain most of the normal matter in the universe, not in the form of stars or planets or anything we can see directly, but as hot, diffuse gas heated to millions of degrees by gravitational compression. This warm, hot intergalactic medium, as scientists call it, glows only in X-ray wavelengths, making it invisible to optical telescopes but detectable by space-based X-ray observatories. Recent observations from ESA's AERO-CETA instrument have directly imaged portions of this cosmic web, showing filaments of hot gas connecting galaxy clusters across vast distances. The temperature of this intergalactic material, often reaching 10 million degrees Kelvin, creates a plasma state where electrons have been stripped from atomic nuclei, forming an ionized medium that fills the space between galaxies. What makes these discoveries even more remarkable is that they reveal structures that have persisted for nearly the entire age of the universe. The patterns Planck detected in the cosmic microwave background are 13.8 billion years old, created when the universe was a tiny fraction of its current size. Yet these same patterns continue to guide the evolution of cosmic structure today. Dark matter, which comprises about 85% of all matter in the universe, follows the gravitational blueprints established in those first few 100,000 years after the Big Bang. Like invisible rivers flowing through space, streams of dark matter carry ordinary matter along, feeding gas to galaxies and determining where new stars will form. The precision of Planck's measurements also revealed something unexpected about the geometry of space itself. The cosmic microwave background shows that space is remarkably flat on the largest scales, neither curved inward, like the surface of a sphere, nor curved outward like a saddle. This flatness extends across regions much larger than anything light could have travelled since the Big Bang, suggesting that the universe underwent a period of extremely rapid expansion in its earliest moments. This inflationary epoch, lasting only a tiny fraction of a second, stretched quantum fluctuations to cosmic scales, creating the temperature variations that Planck detected and that eventually became the cosmic web. Today, as you breathe quietly in the darkness, you are surrounded by this ancient architecture. The cosmic web extends through your location, invisible threads of dark matter and hot gas connecting your neighborhood to structures billions of light years away. The same gravitational forces that shaped the first galaxies continue to influence the motion of matter around you, guiding the slow dance of cosmic evolution that will continue for billions of years to come. Every atom in your body has travelled along these invisible highways, carried by currents established when the universe was younger than a single human lifetime, following pathways illuminated by the oldest light in existence. In the spring of 1933, a Swiss astronomer named Fritz Zwicky made an observation that would haunt physics for the next 90 years. Studying the Coma cluster, a collection of over 1,000 galaxies bound together by gravity, Zwicky measured how fast individual galaxies were moving within the cluster and calculated how much mass would be needed to hold them together. What he discovered defied every expectation about how the universe should work. The galaxies were moving far too quickly, racing through space at velocities that should have flung them out of the cluster and into the cosmic void long ago. According to the laws of gravity that had successfully explained planetary motion for centuries, these galaxies should have dispersed billions of years earlier. Yet there they were, held in a stable configuration by some invisible force. Zwicky calculated that the cluster contained at least 10 times more mass than could be accounted for by all the visible stars and gas combined. He called this unseen material dark matter, coining a term that would become one of the greatest mysteries in science. For decades, Zwicky's discovery remained an isolated puzzle, intriguing but not necessarily indicative of a fundamental gap in our understanding of the cosmos. Many astronomers assumed that hidden gas or faint stars would eventually be found to explain the missing mass. But in the 1970s, a persistent astronomer named Vera Rubin began making observations that would transform this curiosity into a cosmic crisis. Working with a new spectrograph at Palomar Observatory, Rubin measured the rotation speeds of spiral galaxies with unprecedented precision, tracking how fast stars moved at different distances from galactic centers. What she found challenged everything astronomers thought they knew about how galaxies work. In a typical spiral galaxy like our own Milky Way, most of the visible matter is concentrated near the center, where billions of stars cluster around a supermassive black hole. According to Newton's laws, stars farther from this central mass should orbit more slowly, just as the outer planets in our solar system take longer to complete their orbits than Mercury or Venus. The rotation curve of a galaxy should show fast motion near the center and steadily decreasing speeds toward the edges, following the same mathematical relationship that governs planetary motion. But Rubin's observations revealed something completely different. Instead of slowing down at greater distances from galactic centers, stars in the outer regions of spiral galaxies maintain nearly constant velocities, spinning around their galaxies far faster than the visible matter could explain. These outer stars were moving so quickly that they should have been flung into intergalactic space within a few 100 million years, yet galaxies billions of years old showed the same pattern. The only way to explain this phenomenon was to assume that each galaxy was embedded in a vast halo of invisible matter. extending far beyond the visible disk and containing several times more mass than all the observable stars combined. This dark matter halo would provide the additional gravitational pull needed to keep the outer stars bound to their galaxies, but it would have to be made of something that emits no light and interacts with ordinary matter only through gravity. Rubin's work revealed that what Zwicky had detected in galaxy clusters was not an anomaly, but a fundamental feature of cosmic architecture. Every large galaxy appeared to be surrounded by a dark matter halo, roughly 5 times more massive than the galaxy's visible components. These observations meant that the universe contained vastly more matter than anyone had imagined, most of it in a form completely unlike anything in our everyday experience. The birth of the dark matter hypothesis forced astronomers to confront the possibility that they had been studying only a small fraction of the actual universe. If galaxies were embedded in halos of invisible matter, and if these halos extended far into the space between galaxies, then the seemingly empty regions surrounding every visible structure might actually contain most of the mass in the cosmos. This realization opened up profound questions about the nature of matter itself. What could dark matter be made of if it neither emits nor absorbs light? How could something so abundant leave so few traces of its existence? And if the universe contained 5 times more dark matter than ordinary matter, why had it taken so long to discover? These questions launched decades of theoretical work and experimental searches that continue today. Particle physicists proposed exotic new forms of matter that could exist in vast quantities while remaining nearly invisible to our instruments. Cosmologists developed computer simulations showing how dark matter halos could guide the formation of the cosmic web that Planck would later detect. Astronomers began searching for other ways to observe this hidden component of the universe, leading to techniques like gravitational lensing that can map dark matter distributions by observing how they bend light from distant sources. The mystery that began with Zwicky's careful measurements in 1933 had revealed that the space between stars, far from being empty, contains most of the matter in the universe in a form so different from our everyday experience that we are still struggling to understand its true nature. Just this November, nearly a century after Fritz Zwicky first detected the gravitational fingerprints of invisible matter, scientists may have achieved what many considered impossible: the first direct observation of dark matter itself. Professor Tomonori Tatani at the University of Tokyo, analysing 15 years of data from NASA's Fermi Gamma Ray Space Telescope, discovered something extraordinary in the heart of our own galaxy. Using sophisticated techniques to filter out all known sources of gamma radiation, Tatani's team detected a halo of high-energy gamma rays extending toward the centre of the Milky Way, glowing with an energy signature that matches theoretical predictions made decades ago for dark matter particle interactions. These gamma rays carry exactly 20 giga-electron volts of energy, which translates to 20 billion electron volts, an almost incomprehensibly large amount of energy concentrated in individual photons. What makes this discovery so significant is not just the detection of these gamma rays, but their precise characteristics and distribution. The energy level, intensity pattern, and halo-like structure align remarkably well with long-standing models of weakly interacting massive particles, the leading candidates for dark matter that theorists have been predicting since the 1980s. According to these models, when 2 dark matter particles collide in the dense regions near galactic centers, they should annihilate each other in a burst of energy that produces gamma rays with very specific properties. For decades, this remained purely theoretical, a prediction that could not be tested because the expected signals were far too faint for existing instruments to detect. The Fermi telescope, however, has spent 15 years accumulating data with extraordinary sensitivity, and Tatani's analysis represents the first time anyone has been able to separate these faint signals from the overwhelming background of gamma radiation produced by more conventional astrophysical sources like pulsars, supernova remnants, and cosmic ray interactions. The detection process required unprecedented precision because gamma rays are produced throughout the galaxy by numerous energetic phenomena, making it extraordinarily difficult to identify which emissions might come specifically from dark matter interactions. The breakthrough came from focusing on a region near the galactic center, where dark matter should be most concentrated, while carefully accounting for and subtracting all other known sources of gamma radiation in that area. When all conventional sources were removed from the data, what remained was a diffuse glow that could not be explained by any known astrophysical process except dark matter particle annihilation. The energy signature of these gamma rays provides crucial information about the nature of dark matter itself. The 20 GeV energy level suggests that dark matter particles have masses roughly 20 times that of a proton, placing them in the range predicted by supersymmetric particle theories developed over the past several decades. More importantly, the detection confirms that dark matter particles do indeed interact with each other, albeit extremely rarely, and that these interactions produce the gamma-ray signatures that theorists have long predicted. This discovery represents far more than just the identification of a new type of particle. If confirmed by additional observations, it would validate our understanding of how the largest structures in the universe formed and evolved. Dark matter serves as the gravitational scaffolding upon which all cosmic architecture depends, from the formation of the first galaxies to the intricate web-like structure that connects galaxy clusters across billions of light years. Without dark matter providing this invisible framework, galaxies could never have formed quickly enough after the Big Bang to create the universe we observe today. The implications extend to our understanding of cosmic structure on every scale. Dark matter halos surrounding galaxies guide the flow of ordinary matter, determining where gas condenses to form new stars and how galaxies merge and evolve over cosmic time. The cosmic web detected by the Planck satellite represents the visible consequences of dark matter's invisible influence, with filaments of hot gas tracing the underlying dark matter structure that channels matter across vast distances. Tatani himself acknowledges that this detection, while compelling, requires confirmation through additional observations and analysis. The scientific community will demand rigorous verification before accepting that humanity has finally observed dark matter directly after nearly a century of searching. Future observations will need to detect the same gamma-ray signature in other regions where dark matter should be concentrated, such as the dwarf galaxies that orbit our Milky Way. These smaller galaxies are believed to be almost entirely composed of dark matter, making them ideal laboratories for confirming whether the Fermi detection represents genuine dark matter, annihilation, or some previously unknown astrophysical phenomenon. If verified, this breakthrough would mark the beginning of a new era in cosmic observation, where we can finally study the substance that comprises most of the matter in the universe and shapes the evolution of every structure from galactic halos to the cosmic web itself. The universe possesses an architecture so vast and intricate that our minds struggle to comprehend its scale, a cosmic web of invisible matter that connects every galaxy across billions of light-years of space. This scaffolding, built primarily from dark matter, forms the fundamental framework upon which all visible structures depend, creating pathways that channel ordinary matter across distances that dwarf entire galactic superclusters. Recent observations from the Rosetta X-ray telescope have provided the most detailed maps ever created of this cosmic architecture, revealing filaments of hot gas that trace the underlying dark matter structure with unprecedented clarity. These observations show that the space between galaxies, far from being empty, contains a network of matter streams heated to temperatures of 7 million degrees Kelvin, hot enough to strip electrons from atoms and create a plasma that glows brilliantly in X-ray wavelengths. This warm, hot intergalactic medium, which astronomers call WIM, represents one of the major reservoirs of ordinary matter in the universe, containing roughly half of all the protons and neutrons that exist outside of stars and galaxies. The filaments themselves stretch across distances that challenge human comprehension, typically spanning a 50 to 250 megaparsecs from end to end, which translates to between 500 and 800 million light-years. To put this in perspective, if our entire local group of galaxies, including the Milky Way and Andromeda, were reduced to the size of a small town, these cosmic web filaments would stretch across entire continents. The structure emerges from the gravitational influence of dark matter, which comprises roughly 85% of all matter in the universe and serves as the invisible foundation upon which the cosmic web is built. Dark matter particles, whatever their true nature, interact only through gravity, allowing them to form vast halos and filaments without the electromagnetic forces that would cause ordinary matter to radiate away its energy and collapse. These dark matter structures act like cosmic highways, guiding the flow of gas and dust across intergalactic distances and determining where new galaxies will form and how existing galaxies will evolve over billions of years. The Rosetta observations have revealed that the cosmic web is far more complex and dynamic than previously imagined. With multiple filaments intersecting at massive galaxy clusters, and creating nodes where matter concentrates to form some of the largest structures in the observable universe. At these intersection points, the gravitational potential wells created by dark matter concentrations can reach depths equivalent to millions of solar masses, creating environments where gas is compressed and heated to such extreme temperatures that it becomes visible across vast distances in X-ray light. The temperature of the WHIM, reaching 7 million degrees Kelvin in the densest regions, results from gravitational heating as ordinary matter falls into the dark matter. Potential wells that define the cosmic web structure. This process converts gravitational potential energy into thermal energy, creating a plasma state where atomic nuclei and electrons exist separately, moving at velocities that would be impossible at lower temperatures. The density of this intergalactic medium, while extremely low by earthly standards, with fewer than 100 particles per cubic meter, contains enough total mass to account for a significant fraction of the universe's ordinary matter budget. Recent computer simulations have shown that the cosmic web structure we observe today began forming when the universe was only a few 100 million years old, shortly after the first stars began to shine. Dark matter, halos served as gravitational seeds that attracted surrounding matter, gradually building up the filamentary structure through billions of years of cosmic evolution. The process continues today, with gas flowing along these invisible highways to feed star formation in galaxies and sustaining the cosmic recycling system that distributes heavy elements produced in stellar cores across intergalactic distances. Perhaps most remarkably, the cosmic web demonstrates that every region of space, no matter how apparently empty, participates in this grand structure. Even the space around our solar system lies within a cosmic web filament, connected through dark matter, flows to structures billions of light years away. The local group of galaxies occupies a position within a larger filamentary structure that extends toward the Virgo cluster and beyond, making us part of a cosmic highway that channels matter across distances spanning significant fractions of the observable universe. This realization transforms our understanding of cosmic loneliness, revealing that no galaxy exists in true isolation, but rather participates in a universe-spanning network of matter and energy exchange. The dark matter scaffolding that creates this web represents one of the most successful examples of cosmic engineering, a self-organizing system that has operated for over 13 billion years to create the complex hierarchical structure we observe today. From the smallest dwarf galaxies to the largest superclusters, every astronomical structure owes its existence to the invisible architecture of dark matter that continues to guide cosmic evolution on the grandest scales imaginable. Dark matter does not merely exist passively in the space between stars, but actively shapes every aspect of cosmic reality, bending light itself to reveal its presence through one of Einstein's most elegant predictions. Gravitational lensing, the phenomenon where massive objects curve space-time enough to deflect the path of light rays, has become our most powerful tool for mapping dark matter distributions across the universe. When light from distant galaxies passes near regions of concentrated dark matter, it follows the curved geometry of spacetime like a marble rolling along a curved surface, causing background galaxies to appear distorted, magnified, or split into multiple images. By carefully measuring these distortions in thousands of distant galaxies, astronomers can create detailed maps of dark matter halos, revealing structures that would otherwise remain completely invisible. The most dramatic demonstration of dark matter's reality came from observations of the Bullet cluster, formerly known as 1E 0657-56, located 3.8 billion light-years from Earth. This massive system formed when two large galaxy clusters collided in an extraordinarily energetic event that separated ordinary matter from dark matter in ways that could be directly observed. During the collision, the hot gas that fills the space between galaxies in each cluster interacted electromagnetically, slowing down and creating shock waves that heated the material to temperatures exceeding 100 million degrees. This hot gas, visible in X-ray observations from NASA's Chandra telescope, shows where the ordinary matter ended up after the collision. But gravitational lensing observations from the Hubble Space Telescope revealed something remarkable. The majority of each cluster's mass, mapped through its gravitational effects on background galaxies, had passed right through the collision site without slowing down. The dark matter halos of the two clusters, unaffected by electromagnetic forces, had sailed past each other, while the ordinary matter lagged behind. creating a clear spatial separation between where most of the mass actually resides and where the visible matter accumulated. This observation provided compelling evidence that dark matter consists of particles that interact only gravitationally, passing through ordinary matter and even through each other without electromagnetic interference. The role of dark matter in galaxy formation extends far beyond providing gravitational scaffolding for cosmic structure. Computer simulations of the early universe show that without dark matter, galaxies could never have formed quickly enough to create the universe we observe today. In the first few 100,000 years after the Big Bang, ordinary matter was too hot and too strongly coupled to radiation to begin collapsing under its own gravity. But dark matter, unaffected by electromagnetic forces, could begin forming gravitational wells immediately after the universe became matter-dominated. These dark matter concentrations provided the seeds around which ordinary matter could eventually condense once the universe cooled sufficiently for atoms to form and radiation to decouple from matter. The hierarchical structure formation process that followed created dark matter halos of various sizes, from the smallest dwarf galaxy halos containing the mass of a few million suns to the largest cluster halos weighing as much as 1,000 trillion suns. Each galaxy we observe today formed within one of these dark matter halos, with the halo's mass determining many of the galaxy's fundamental properties, including its size, star formation rate, and ability to retain gas for future star formation. Dark matter halos also serve a protective function that proves essential for galaxy survival and evolution. The cosmic web through which galaxies move contains high-energy cosmic ray particles and intense radiation from various sources that could strip away a galaxy's gas content and halt star formation entirely. Dark matter halos provide gravitational wells deep enough to retain this gas against the disruptive effects of cosmic radiation, while also deflecting some of the most energetic particles that might otherwise sterilize galactic environments. This protective effect becomes particularly important for smaller galaxies, which have shallower gravitational wells and would be more vulnerable to losing their star-forming material without the additional gravitational binding provided by their dark matter halos. The influence of dark matter on cosmic structure formation can be traced back to quantum fluctuations in the very early universe, tiny variations in density that were stretched to cosmic scales during the inflationary epoch that preceded normal cosmic expansion. These primordial fluctuations, preserved in the cosmic microwave background that Planck observed, provided the initial conditions for dark matter structure formation. Regions that were slightly denser than average attracted more dark matter through gravitational instability, growing larger and denser over cosmic time until they became the halos and filaments we observe today. This process demonstrates that dark matter connects the smallest quantum scales to the largest cosmic structures, translating microscopic uncertainties from the first fraction of a second after the Big Bang into the cosmic web that spans billions of light years and guides the evolution of every galaxy in the observable universe. In 2024, the James Webb Space Telescope revealed one of the most surprising discoveries about the space between stars, detecting magnetic field structures so intricate and powerful that they fundamentally changed our understanding of how the cosmos organizes itself on the smallest observable scales. The breakthrough came from observations of the Serpens Nebula, a star-forming region 1,300 light-years from Earth, where Webb's unprecedented infrared vision captured something that had never been directly observed before. A group of newborn stars whose jets and outflows were all perfectly aligned in the same direction, like cosmic weather vanes pointing towards some invisible organizing force. These protostellar outflows form when material falling onto a young star gets caught in powerful magnetic fields and launched outward as twin jets traveling at hundreds of miles per second. Normally, these jets point in random directions because each star forms independently with its own magnetic field orientation. But in the northern region of the Serpens Nebula, Webb detected dozens of these outflows all tilted at precisely the same angle, revealing the presence of a large-scale magnetic field that was guiding star formation across the entire region. The jets themselves appear as bright streaks of red light in Webb's infrared images, marking shockwaves created when high-speed gas collides with the surrounding interstellar medium, and the fact that these streaks all run parallel to each other indicates that magnetic forces were organizing stellar birth on scales never before observed directly. Webb's near-infrared camera was able to resolve structures as small as 400 astronomical units which is less than 1/100th of a light year, revealing that magnetic fields create coherent patterns even on these tiny scales within stellar nurseries. This discovery demonstrated that the magnetic skeleton of the cosmos extends down to the level of individual star formation, shaping not just galactic-scale phenomena, but the birth of every star and planetary system. Even more remarkable were Webb's observations of the Cassiopeia supernova remnant, where a different kind of magnetic revelation emerged from studying light echoes created when the supernova's flash illuminated surrounding interstellar dust clouds. These observations revealed sheet-like structures in the interstellar medium that had never been detected before, along with dense, tightly wound regions that resembled knots in wood grain. Scientists interpreting these images concluded that the sheet-like structures were likely shaped by interstellar magnetic fields, while the knotted regions represented magnetic islands embedded within the broader magnetic field that fills the space between stars. The precision of Webb's observations allowed astronomers to create what they described as the astronomical equivalent of a medical CT scan, providing three-dimensional views of magnetic field structure by observing the same region at different times as the light echo passed through it. These observations showed that the interstellar medium possesses a complex magnetic architecture that extends throughout the galaxy, creating invisible highways along which charged particles travel and organizing the flow of gas and dust on scales ranging from hundreds of astronomical units to thousands of light years. The magnetic fields Webb detected are not mere curiosities but fundamental forces that control some of the most important processes in cosmic evolution. In star-forming regions, magnetic fields determine how quickly gas can collapse to form new stars, sometimes supporting the gas against gravitational collapse and sometimes channeling material toward forming stellar systems. The magnetic field strength in these regions often equals or exceeds the energy density of turbulent gas motions, making magnetism a dominant force in determining where and how stars will form. Webb's observations of the Sagittarius C region near the center of our galaxy revealed another aspect of cosmic magnetism, showing how the extreme gravitational environment around our galaxy's supermassive black hole can stretch and amplify magnetic fields to strengths that completely dominate the behavior of surrounding gas. In this region, magnetic forces were strong enough to prevent gas from collapsing to form new stars despite the presence of dense molecular clouds that would normally be prime stellar nurseries. The magnetic fields instead confined the hot plasma into long filaments that glow brilliantly in infrared light, creating structures that remain stable against both gravitational collapse and pressure-driven expansion. These discoveries revealed that magnetic fields in the galactic center reach intensities trillions of times stronger than Earth's magnetic field, creating an environment where electromagnetic forces overwhelm gravity in determining how matter behaves. Webb's ability to observe these magnetic phenomena represents a breakthrough in our capacity to study one of the most important but previously invisible components of cosmic structure, opening new avenues for understanding how the universe organizes matter and energy on every scale from individual star systems to entire galaxies. Throughout the vast expanse of our Milky Way galaxy, an invisible electromagnetic skeleton threads through every cubic meter of space, creating magnetic highways that guide the motion of charged particles across distances spanning tens of thousands of light years. This galactic magnetic field, while incredibly weak by terrestrial standards, possesses a cumulative strength that dwarfs Earth's magnetosphere by factors of trillions when considered across its full extent, creating one of the most powerful and influential forces shaping cosmic evolution. The architecture of this magnetic network resembles a cosmic circulatory system, with field lines spiraling outward from the galactic center and following the rotation of stellar populations, while also threading vertically through the galactic disk to connect with magnetic fields in the surrounding halo. Recent observations by radio telescopes have mapped this structure in unprecedented detail, revealing that magnetic field lines extend far beyond the visible edge of our galaxy and connect our stellar neighborhood to the broader cosmic web through electromagnetic pathways that span intergalactic distances. Within this grand magnetic architecture, certain regions stand out for their extraordinary field strength and dramatic influence on stellar evolution. The Sagittarius C stellar nursery, located near the center of our galaxy, provides one of the most striking examples of how intense magnetic fields can completely dominate the behavior of interstellar gas. In this region, the gravitational influence of our galaxy's supermassive black hole Sagittarius A, creates tidal forces that stretch and amplify magnetic fields to strengths approaching those found in the atmospheres of neutron stars. These amplified fields become so powerful that they can overcome the gravitational attraction that normally causes dense gas clouds to collapse and form new stars. Instead of stellar birth, the magnetic forces confine hot plasma into long, twisted filaments that remain suspended in space, glowing with the light of charged particles spiraling along magnetic field lines. This magnetic suppression of star formation represents one of the most dramatic examples of electromagnetic forces controlling galactic evolution, effectively sterilizing regions that should otherwise be among the most prolific stellar nurseries in the galaxy. The magnetic field lines themselves serve as cosmic highways for some of the most energetic particles in the universe. Cosmic rays, which are charged particles accelerated to speeds approaching the speed of light, cannot travel in straight lines through magnetized space, but instead follow spiral paths around magnetic field lines like charged particles in a cosmic accelerator. This process confines cosmic rays within our galaxy for millions of years, allowing them to accumulate to energy densities that rival the thermal energy of interstellar gas and the gravitational binding energy of molecular clouds. As these particles spiral along magnetic highways, they gradually lose energy through interactions with starlight and magnetic fields. But they also gain energy through encounters with shock waves from supernova explosions and through magnetic reconnection events that can suddenly release vast amounts of stored magnetic energy. Magnetic reconnection represents one of the most explosive phenomena occurring continuously throughout interstellar space, happening when magnetic field lines with opposite orientations encounter each other and suddenly snap together, converting magnetic energy into kinetic energy with extraordinary efficiency. These reconnection events can accelerate particles to cosmic ray energies within seconds, creating some of the highest energy particles observed anywhere in the universe. The process occurs most dramatically near the galactic center, where the complex magnetic environment around Sagittarius A creates countless opportunities for field lines to interact and reconnect. But it also happens throughout the galactic disk, whenever supernova shock waves or stellar winds disturb the otherwise smooth magnetic field structure. Radio telescopes observing synchrotron radiation from electrons spiraling in magnetic fields have revealed that these reconnection events create extended regions of enhanced magnetic activity that can persist for thousands of years, gradually spreading outward through the galactic magnetic field network and influencing star formation and cosmic ray propagation across vast regions of space. The galactic magnetic field also plays a crucial role in regulating the exchange of matter and energy between our galaxy and the surrounding intergalactic medium. Magnetic pressure helps support gas in the galactic halo against gravitational collapse, while magnetic tension can channel infalling gas along preferred directions, guiding the accretion process that feeds ongoing star formation in the galactic disk. Observations of other spiral galaxies show similar magnetic architectures, suggesting that large-scale magnetic fields represent a universal feature of galaxy evolution, with field strengths and geometries that correlate strongly with galactic rotation rates, star formation activity, and the presence of central supermassive black holes. This magnetic component of cosmic structure connects the smallest scales of particle physics to the largest scales of galactic dynamics, creating a unified electromagnetic environment that influences everything from the formation of individual stars to the overall evolution of galactic ecosystems across billions of years of cosmic time. Space itself possesses a form of electromagnetic memory that stretches back to the earliest moments of cosmic history, preserved in magnetic fields that have woven themselves into the fabric of the universe since long before the first stars began to shine. These primordial magnetic fields, generated in the first fraction of a second after the Big Bang through quantum fluctuations and phase transitions in the early universe plasma, have survived for over 13 billion years as a kind of cosmic DNA that still influences the evolution of galaxies and the large-scale structure we observe today. Recent theoretical work suggests that these ancient magnetic fields may hold the key to resolving one of the most perplexing mysteries in modern cosmology, the Hubble tension, which describes the disagreement between different measurements of how fast the universe is expanding. Some cosmologists now propose that primordial magnetic fields could have provided an additional source of pressure in the early universe that slightly altered the expansion rate, creating subtle effects that persist in today's cosmic microwave background, and might explain the discrepancies between local and distant measurements of cosmic expansion. The presence of these magnetic fields throughout cosmic history can be traced through the synchrotron radiation they produce when charged particles spiral around magnetic field lines at near light speeds, creating a glow that spans the entire electromagnetic spectrum from radio waves to gamma rays. This synchrotron emission serves as a cosmic lighthouse that reveals the locations and strengths of magnetic fields across vast distances, allowing astronomers to map magnetic structures that would otherwise remain completely invisible. Radio telescopes observing at frequencies between a few megahertz and several gigahertz have detected this synchrotron glow throughout our galaxy and in galaxies billions of light years away, showing that magnetic fields represent a fundamental component of cosmic structure on every scale, from individual star-forming regions to entire galaxy clusters. The radio sky reveals an intricate network of filamentary structures that trace magnetic field lines throughout the Milky Way, creating patterns that look remarkably similar to the neural networks in biological systems, or the filamentary structure of the cosmic web itself. These radio filaments extend for hundreds of light years through interstellar space, marking regions where magnetic fields have been amplified by stellar winds, supernova explosions, or gravitational interactions with massive objects like the supermassive black hole at our galactic center. Some of these structures appear to be connected across vast distances, suggesting that the galactic magnetic field possesses a coherent large-scale organization that has persisted for hundreds of millions of years, despite the turbulent environment of star formation, stellar death, and galactic rotation, that continuously reshapes the distribution of matter in our galaxy. The electrons responsible for synchrotron radiation must be continuously replenished because they lose energy rapidly through electromagnetic interactions, meaning that the radio filaments we observe represent active regions where cosmic ray particles are being accelerated to extreme energies by magnetic reconnection events, shock waves, or other violent processes. This ongoing particle acceleration creates a dynamic magnetic environment where field lines constantly reconfigure themselves in response to stellar explosions and gravitational disturbances, while somehow maintaining the overall coherent structure that connects local magnetic phenomena to the galaxy-wide magnetic architecture. Observations of distant galaxies show that similar magnetic structures existed when the universe was only a few billion years old, indicating that magnetic field amplification and organization represent fundamental processes that began operating shortly after the first galaxies formed. The magnetic memory preserved in these ancient field configurations provides information about conditions in the early universe that cannot be obtained from any other source, including details about the physics of cosmic phase transitions, the nature of dark matter interactions, and the processes that generated the first cosmic structures. Computer simulations of galaxy formation that include magnetic fields show dramatically different evolutionary pathways compared to simulations that ignore magnetism, with magnetic pressure and tension affecting everything from the rate of star formation to the morphology of galactic disks and the efficiency of gas accretion from the intergalactic medium. These simulations reveal that magnetic fields can suppress star formation in some environments while enhancing it in others, creating complex feedback loops that influence galactic evolution over billions of years and may explain many of the observed correlations between galactic properties and environment. The study of cosmic magnetism has also revealed that magnetic fields can store and transport energy across galactic distances with remarkable efficiency, creating a form of electromagnetic weather that influences conditions throughout entire galactic ecosystems. Magnetic storms triggered by supernova explosions or stellar collisions can propagate along field lines at speeds approaching the speed of light, carrying energy and momentum to regions thousands of light years away from the original disturbance, and creating coordinated changes in star formation activity across vast regions of space. This magnetic connectivity means that events occurring in one part of a galaxy can influence conditions throughout the entire system, creating a level of cosmic organization and communication that operates through purely electromagnetic processes and represents one of the most important but least understood aspects of how galaxies function as integrated systems rather than collections of independent stellar populations. Right now, as you rest quietly in the darkness, an invisible flood of ghostly particles is dreaming through your body at a rate that defies imagination, with roughly 65 billion neutrinos passing through every square centimetre of your skin each second without leaving the slightest trace of their passage. These neutrinos, the most abundant particles with mass in the universe, fill every cubic centimetre of space around you. travelling at speeds approaching the speed of light and carrying information from some of the most extreme environments in the cosmos. For decades, detecting these elusive messengers seemed nearly impossible because neutrinos interact so weakly with ordinary matter that they can pass through entire planets without being stopped, making them incredibly difficult to observe despite their overwhelming abundance. The breakthrough came from the IceCube Neutrino Observatory, a revolutionary detector that transformed a cubic kilometre of pristine Antarctic ice into the largest neutrino telescope ever built, using the entire South Pole as a cosmic ray shield to filter out unwanted background radiation. IceCube works by detecting the faint flashes of blue light produced when neutrinos occasionally interact with water molecules in the ice, creating charged particles that travel faster than light can propagate through the dense medium and produce Cherenkov radiation that can be captured by thousands of sensitive photodetectors buried deep beneath the surface. In 2013, this extraordinary instrument achieved something that had been sought for decades: the first detection of high-energy neutrinos originating from beyond our solar system, opening an entirely new window for observing the universe through particles rather than light. These cosmic neutrinos carry energies millions of times greater than those produced in the nuclear fusion reactions powering the Sun, indicating that they originated from some of the most violent and energetic processes occurring anywhere in the observable universe. The discovery transformed neutrino astronomy from a theoretical possibility into an observational reality, providing a new way to study cosmic phenomena that remain hidden from conventional telescopes because they occur in regions opaque to electromagnetic radiation, or because they involve processes that produce few or no photons. The significance of this breakthrough became even more apparent in 2023 when IceCube scientists announced the detection of neutrinos originating from within our own Milky Way galaxy, specifically from interactions between cosmic rays and the interstellar medium along the galactic plane. This detection required sophisticated machine learning techniques to analyze 10 years of accumulated data, sifting through 60,000 neutrino events to identify those with the characteristic energy distribution and directional patterns expected from galactic sources. The neutrino emissions from the galactic plane matched the pattern of gamma-ray emissions detected by the Fermi Space Telescope, confirming theoretical predictions that cosmic ray interactions with interstellar gas should produce both neutrinos and gamma rays through the decay of short-lived particles called pions. This correlation between neutrino and gamma-ray observations provided compelling evidence that neutrinos can serve as reliable tracers of cosmic ray acceleration sites, revealing the locations of natural particle accelerators that boost cosmic rays to energies far exceeding anything achievable in human-built accelerators. The field of neutrino astronomy reached another milestone in 2024 when the KM3NET experiment, a neutrino telescope under construction in the Mediterranean Sea, detected the most energetic cosmic neutrino ever observed, carrying more than 100 peta-electron volts of energy, which is roughly 100 times more energetic than the highest energy neutrinos previously detected by IceCube. This record-breaking detection occurred during the early phases of KM3NET construction, when only a fraction of the planned detector array was operational, suggesting that the full detector will reveal neutrino sources and phenomena that remain completely unknown. The extraordinary energy of this neutrino indicates that it likely originated from one of the universe's most extreme environments, possibly an active galactic nucleus, where matter falling into a supermassive black hole creates relativistic jets that can accelerate particles to energies approaching theoretical limits. Unlike cosmic ray particles, which are deflected by magnetic fields during their journey through space and arrive at Earth from seemingly random directions, neutrinos travel in perfectly straight lines from their sources, making them ideal messengers for pinpointing the locations of cosmic ray acceleration sites and studying the physics of extreme astrophysical environments. The neutrino flood that surrounds us represents more than just a curiosity of particle physics. It provides a direct connection to processes occurring throughout the universe, from the nuclear fusion reactions in stellar cores to the most violent explosive events involving black holes and neutron stars. Every neutrino carries within its energy and direction information about conditions at its source, creating an invisible library of cosmic information that flows continuously through space and offers insights into phenomena that cannot be studied through any other means of observation. After decades of detecting neutrinos from unknown cosmic sources, astronomers achieved a historic breakthrough when they identified the first specific celestial object responsible for producing high-energy neutrinos reaching Earth. NGC 1068, also known as Messier 7, a spiral galaxy located 47 million light-years away in the constellation Cetus. This discovery emerged from a careful analysis of 10 years of IceCube data, during which scientists detected 80 neutrino events with energies in the tera-electronvolt range, all originating from the same small patch of sky where NGC 1068 resides. The statistical significance of this clustering was so overwhelming that it could occur by chance less than once in several million random trials, providing the first definitive evidence that specific galaxies serve as cosmic neutrino factories operating on timescales spanning decades or longer. NGC 1068 belongs to a class of objects called active galactic nuclei, where a supermassive black hole millions of times more massive than our Sun feeds on surrounding matter and launches powerful jets of particles at velocities approaching the speed of light. These jets create natural particle accelerators far more powerful than anything humans have ever built, boosting protons and heavier atomic nuclei to energies that exceed the most energetic cosmic rays detected at Earth by factors of thousands or millions. When these ultra-high energy particles collide with dense clouds of gas surrounding the central black hole, they produce showers of secondary particles, including neutrinos that carry away a significant fraction of the original particle energy. The neutrinos escape from these dense environments because they interact so weakly with matter, allowing them to travel across tens of millions of light-years of space without being absorbed or deflected, carrying direct information about the extreme physics operating near supermassive black holes. The detection of neutrinos from NGC 1068 was particularly significant because this galaxy appears relatively quiet in gamma-ray observations, indicating that the region where neutrinos are produced remains hidden behind thick clouds of gas and dust that absorb electromagnetic radiation, but allow neutrinos to pass through unimpeded. This discovery demonstrated that neutrino astronomy can reveal cosmic ray acceleration sites that remain completely invisible to conventional telescopes, opening new avenues for studying the most energetic processes in the universe. The success with NGC 1068 built upon earlier multi-messenger discoveries, particularly the detection in 2017 of neutrinos from the Blazar TXS 64056, a more distant active galaxy whose relativistic jet happens to point directly toward Earth. When IceCube detected a high-energy neutrino from the direction of this blazar, the observatory immediately sent automated alerts to telescopes around the world, triggering follow-up observations across the electromagnetic spectrum from radio waves to gamma rays. These coordinated observations revealed that the blazar was undergoing a period of enhanced activity precisely when the neutrino arrived, providing compelling evidence that the same acceleration processes responsible for the electromagnetic emissions were also producing high-energy neutrinos. The multi-messenger approach proved so successful that it has become the standard method for investigating cosmic neutrino sources, combining neutrino detections with simultaneous observations by gamma-ray telescopes, optical telescopes, and radio arrays to build comprehensive pictures of how particle acceleration works in extreme astrophysical environments. These discoveries have revealed that active galactic nuclei represent a major class of cosmic ray accelerators, possibly accounting for a significant fraction of the ultra-high energy cosmic rays that regularly bombard Earth from extragalactic sources. The neutrinos detected from these distant galaxies carry energies hundreds of times greater than those produced in the most powerful particle accelerators on Earth, demonstrating that nature has found ways to concentrate electromagnetic and gravitational forces with extraordinary efficiency. The acceleration mechanisms operating in these cosmic environments remain only partially understood, but they appear to involve complex interactions between magnetic fields, plasma turbulence, and the intense radiation fields surrounding supermassive black holes. Theoretical models suggest that particles can be accelerated through multiple stages, first by shockwaves in the jets themselves, then by magnetic reconnection events where field lines snap together and release enormous amounts of stored energy, and finally through interactions with the intense radiation from the accretion disk surrounding the central black hole. Each stage in this acceleration process can boost particle energies by factors of hundreds or thousands, eventually creating cosmic rays with energies so extreme that they approach theoretical limits imposed by interactions with the cosmic microwave background radiation. The neutrinos produced by these ultra-high energy cosmic rays serve as direct probes of acceleration physics under conditions that cannot be reproduced in laboratory experiments, providing unique insights into fundamental processes that shape the most energetic phenomena in the observable universe, and revealing how supermassive black holes transform gravitational energy into the highest energy particles ever detected. The space around us glows with an invisible neutrino radiance that maps the exact same structure revealed by gamma-ray telescopes, creating a ghostly duplicate of our galaxy that can only be detected through the most sophisticated particle physics experiments ever deployed. This galactic neutrino emission, first detected by IceCube in 2003 after analysing a decade of accumulated data, originates from the continuous bombardment of interstellar gas by high-energy cosmic ray particles that have been accelerated by supernova explosions, stellar winds, and other violent processes throughout the Milky Way's 13 billion-year history. When these cosmic rays, which are primarily protons and heavier atomic nuclei, moving at speeds approaching the speed of light, collide with the hydrogen and helium atoms that fill the space between stars, they create showers of secondary particles through nuclear interactions that mirror the processes occurring in the most powerful particle accelerators on Earth. The most important of these secondary particles are unstable subatomic particles called pions, which exist for only a few billionths of a second, before decaying into pairs of other particles that include both neutrinos and the photons responsible for gamma-ray emissions. This shared origin explains why the neutrino glow detected by IceCube matches so precisely the galactic gamma-ray emissions mapped by NASA's Fermi Gamma-Ray Space Telescope, with both forms of radiation following the same distribution along the galactic plane, where cosmic ray densities and interstellar gas concentrations reach their highest values. The discovery required extraordinary precision in data analysis, because neutrino signals from galactic sources are much weaker than those from distant extragalactic objects, and they must be separated from a constant background of neutrinos produced when cosmic rays interact with Earth's atmosphere. Scientists solved this challenge by focusing on cascade events, where incoming neutrinos transfer all their energy to a small volume of ice, creating spherical bursts of light that are easier to distinguish from the elongated tracks produced by atmospheric neutrino interactions. Machine learning algorithms trained on millions of simulated neutrino interactions were able to identify the subtle patterns that distinguish galactic neutrino events from background noise, ultimately revealing that about 10% of the total high-energy neutrino flux reaching Earth originates from cosmic ray interactions within our own galaxy. This galactic contribution represents a significant component of the neutrino sky, providing a new way to study the distribution and energy spectrum of cosmic rays throughout the Milky Way by observing their neutrino byproducts rather than trying to detect the cosmic rays themselves, which are deflected by magnetic fields and arrive from seemingly random directions. The neutrino observations complement cosmic ray measurements by revealing the locations where cosmic ray interactions actually occur, showing how these energetic particles propagate through the complex magnetic environment of our galaxy and interact with different phases of the interstellar medium. Dense molecular clouds, where hydrogen molecules provide abundant targets for cosmic ray collisions, appear as bright sources of neutrino emission, while regions of hot, ionized gas produce fewer neutrinos because of their lower particle densities. This differential neutrino production creates a detailed map of interstellar matter distribution that cannot be obtained through any other observational technique, revealing structures in the galactic gas distribution that remain hidden from direct observation because they emit no light of their own. The sensitivity required to detect this faint galactic neutrino glow pushes current detector technology to its absolute limits, but future experiments promise to revolutionize our ability to study cosmic ray interactions throughout the galaxy. IceCube Gen 2, currently in the planning stages, will expand the detector volume to more than 10 cubic kilometers of instrumented ice, providing roughly 10 times better sensitivity for detecting galactic neutrino sources and potentially revealing individual supernova remnants, pulsar wind nebulae, and other cosmic ray acceleration sites that remain below the detection threshold of current instruments. This next-generation detector will also be sensitive to much lower neutrino energies, allowing astronomers to study cosmic ray interactions across a broader range of particle energies and potentially detecting neutrino emission from stellar processes that operate at lower energies than the extreme phenomena currently accessible through neutrino astronomy. The expanded detector will include thousands of additional photodetectors distributed throughout a much larger volume of Antarctic ice, along with new types of sensors designed to detect different flavors of neutrino interactions and measure their properties with greater precision. These technical advances will enable detailed studies of how cosmic rays propagate through different galactic environments, how they interact with magnetic fields and turbulent gas motions, and how they contribute to the energy balance and chemical evolution of the interstellar medium over cosmic timescales that span billions of years of galactic history. For decades, astronomers faced one of the most embarrassing problems in cosmology. They could account for less than half of the ordinary matter that should exist in the universe according to the predictions of Big Bang nucleosynthesis, the theory that explains how the first atomic nuclei formed in the minutes following cosmic creation. Stars, galaxies, gas clouds, and all other visible structures contained only about 40% of the protons and neutrons that theoretical calculations said should have been created during the universe's first few minutes, leaving scientists to wonder where the remaining 60% of normal matter could be hiding. The solution to this missing boson problem emerged through X-ray observations that revealed vast reservoirs of hot ionized gas filling the space between galaxies, gas so diffuse and hot that it had remained invisible to previous generations of telescopes designed to detect cooler, denser forms of matter. This warm-hot intergalactic medium, which astronomers now call HIM, exists at temperatures between 100,000 and 10 million degrees Kelvin, hot enough to strip electrons from atomic nuclei and create a plasma state where matter glows primarily in X-ray wavelengths rather than visible light. The discovery of HIM solved the missing baryon problem by showing that roughly 50% of all normal matter in the universe resides in this hot, tenuous gas that fills the cosmic web, filaments connecting galaxies across billions of light-years of space. Recent mapping by the Rosetta X-ray telescope, which completed the first all-sky survey in the soft X-ray band with unprecedented sensitivity, has provided the most detailed views ever obtained of this intergalactic medium, revealing a complex network of hot gas filaments that trace the underlying dark matter structure with remarkable precision. The Rosetta observations show that these gas filaments extend for hundreds of millions of light-years between galaxy clusters, creating bridges of million-degree plasma that connect the largest gravitational structures in the universe. The temperature of this intergalactic gas results from gravitational heating as ordinary matter falls into the gravitational potential wells created by dark matter filaments, converting gravitational potential energy into thermal energy through a process similar to what happens when gas falls toward massive objects like stars or black holes, except occurring on scales billions of times larger. The density of HIM, while extraordinarily low by terrestrial standards with fewer than 100 particles per cubic meter, becomes significant when integrated over the enormous volumes of space that these filaments occupy. When scientists calculate the total mass of gas contained in cosmic web filaments mapped by Rosetta, they find that it accounts for the missing baryons that had eluded detection for so long, finally completing the cosmic census of ordinary matter and confirming that our understanding of Big Bang nucleosynthesis was correct all along. The baryon density in these filaments reaches values roughly 76 times higher than the average density of normal matter throughout the universe, creating regions where the cosmic web becomes visible through X-ray emission, while still maintaining the overall filamentary structure predicted by dark matter simulations. This hot intergalactic gas plays a crucial role in cosmic evolution by serving as a reservoir of material that can eventually flow into galaxies to fuel ongoing star formation, while also carrying energy and heavy elements produced in stellar cores across vast distances through the cosmic web. The process of shock heating that creates these high temperatures occurs when gas flowing along dark matter filaments encounters the gravitational potential wells of galaxy clusters and groups, creating bow shocks similar to those formed when supersonic aircraft break the sound barrier, except operating in the tenuous plasma environment of intergalactic space. These shock waves can accelerate gas to velocities of thousands of kilometers per second, generating temperatures high enough to ionize even the heaviest atomic nuclei and creating some of the most extreme plasma conditions anywhere in the universe outside of stellar interiors. The Rosetta survey has revealed that the cosmic web contains temperature variations that reflect the complex dynamics of structure, formation, with the hottest regions reaching temperatures exceeding 10 million Kelvin near massive galaxy clusters, while cooler regions with temperatures around 100,000 Kelvin mark the outer boundaries of cosmic web filaments where gas densities drop toward the average intergalactic value. This temperature structure provides a fossil record of how cosmic structures assembled through gravitational collapse over billions of years, preserving information about the timing and intensity of structure formation processes that shape the universe we observe today. The discovery that most ordinary matter exists in this hot, diffuse state between galaxies fundamentally changed our understanding of cosmic evolution by revealing that the space between visible structures contains not emptiness, but rather the majority of atoms in the universe, heated to extreme temperatures and organized into the largest coherent structures known to exist. Throughout the vast expanse between galaxies, rivers of superheated plasma flow along invisible dark matter highways at velocities exceeding 1,000 kilometers per second, creating streams of million-degree gas that connect every galaxy cluster to the cosmic web and fuel the ongoing process of cosmic evolution. These flows follow the gravitational channels carved by dark matter filaments, with gas accelerating as it falls deeper into the gravitational potential wells and heating up through shock compression until it reaches temperatures comparable to those found in the outer layers of stellar atmospheres. The process begins when primordial gas left over from the Big Bang encounters the gravitational influence of dark matter structures, causing initially cool hydrogen and helium to stream toward regions of higher dark matter density along paths that span hundreds of millions of light years. As this gas moves through the cosmic web, it encounters shock fronts where fast-moving material collides with slower gas that has already begun to accumulate in filamentary structures, creating discontinuities in temperature, pressure, and density that can heat gas from a few degrees above absolute zero to temperatures exceeding 10 million Kelvin in a matter of thousands of years. This shock heating represents one of the most efficient energy conversion processes operating on cosmic scales, transforming the gravitational potential energy stored in dark matter distributions into thermal energy that makes intergalactic gas visible through X-ray emission and creates the plasma conditions necessary for complex chemical and physical processes that cannot occur in cooler environments. The heated gas does not simply accumulate in cosmic web filaments, but continues flowing toward the massive galaxy clusters that mark intersections in the cosmic web, where multiple filaments converge and create the deepest gravitational potential wells in the universe. Around individual galaxies, this hot intergalactic medium creates what astronomers call the circumgalactic medium, a halo of million-degree plasma that extends far beyond the visible stellar disk and serves as a reservoir of material that can eventually cool and condense to fuel ongoing star formation. The circumgalactic medium represents a crucial component of galactic ecosystems because it regulates the rate at which galaxies can continue forming new stars by controlling the supply of fresh gas available for stellar birth. Computer simulations show that without this hot gas reservoir, most galaxies would have exhausted their internal gas supplies billions of years ago and ceased forming new stars, but the continuous inflow of material from the cosmic web allows galaxies to maintain active stellar populations across most of cosmic history. Direct evidence for these hot gas flows comes from observations of quasar absorption lines, where light from distant quasars passes through intervening gas clouds and reveals their temperatures, densities, and chemical compositions through characteristic absorption features in quasar spectra. These absorption line studies have detected hot gas clouds with temperatures ranging from 100,000 to several million degrees, distributed throughout the space between galaxies, often in regions where no visible structures exist but where simulations predict cosmic web filaments should be located. The gas revealed by these observations contains not only primordial hydrogen and helium, but also heavier elements like carbon, nitrogen, and oxygen that were produced in stellar cores and dispersed into the intergalactic medium by supernova explosions and galactic winds, creating a chemical record of billions of years of stellar evolution spread across cosmic distances. Recent technological breakthroughs have enabled the first direct imaging of cosmic web gas through observations by the Condor Array Telescope, a specialized instrument designed to detect extremely faint emission from hot plasma in intergalactic space. These observations have revealed filamentary structures of glowing gas that connect galaxy clusters across distances exceeding 50 million light-years, providing visual confirmation of theoretical predictions about cosmic web architecture that had previously been testable only through computer simulations. The images show that cosmic web filaments are not uniform tubes of gas, but complex structures with varying temperatures, densities and flow patterns that reflect the turbulent dynamics of structure formation and the influence of feedback processes from galaxy formation and black hole activity. Some filaments appear to be actively channeling gas toward massive galaxy clusters, while others show evidence of outflows driven by energy injection from active galactic nuclei or supernova feedback, creating a complex network of inflows and outflows that regulates the cosmic cycle of matter and energy. The temperatures observed in these directly imaged filaments match the predictions of shock heating models, confirming that gravitational energy provides the primary source of heating for intergalactic gas and validating decades of theoretical work on cosmic web physics. These discoveries reveal that the space between galaxies, rather than being empty, contains active flows of matter and energy that connect every visible structure in the universe through a dynamic network of plasma streams operating at temperatures and velocities that place them among the most extreme environments accessible to astronomical observation. Within our own galaxy, the space between stars contains multiple layers of gas and dust existing simultaneously in dramatically different physical states, creating a complex ecosystem where matter cycles continuously between cold molecular clouds, warm atomic gas, and million-degree plasma heated by stellar explosions and stellar winds. This interstellar medium represents one of the most dynamic and multifaceted environments in the universe, with temperatures ranging from just a few degrees above absolute zero in the densest molecular clouds to over 1,000,000 degrees in the hot coronal gas that extends thousands of parsecs above the galactic disk. The coldest component consists of molecular hydrogen clouds, where temperatures drop to 10 to 50 degrees Kelvin, cold enough for molecules to form and survive despite the harsh radiation environment of interstellar space, creating the nurseries where new stars condense from gravitationally collapsing gas over periods of millions of years. These molecular clouds exist in a delicate balance with the warm neutral medium, which maintains temperatures around 8,000 degrees Kelvin and contains most of the atomic hydrogen in the galaxy, providing the reservoir of material that can be compressed and cooled to form the molecular phase when density fluctuations or shock waves create appropriate conditions. Surrounding both of these cooler phases is the warm ionized medium at temperatures near 8,000 degrees, where ultraviolet radiation from hot stars has stripped electrons from hydrogen atoms to create a partially ionized plasma that fills much of the volume between stellar systems. The most spectacular manifestations of interstellar ionization occur in HII regions, where newly formed massive stars heat surrounding gas to temperatures exceeding 10,000 degrees Kelvin through intense ultraviolet radiation, creating glowing nebulae like the Orion Nebula that can be seen across vast distances because of their brilliant emission line spectra. These ionized regions represent sites of recent star formation, where the most massive stars, which burn their nuclear fuel rapidly and emit enormous amounts of high-energy radiation, ionize hydrogen across volumes spanning hundreds of light years before exhausting their fuel supplies and exploding as supernovas. When these massive stars reach the end of their lives, they inject tremendous amounts of energy into the surrounding interstellar medium through supernova, explosions that create expanding shock waves traveling at velocities of thousands of kilometers per second. These supernova shock waves sweep up surrounding gas and heat it to temperatures exceeding 1,000,000 degrees, creating bubbles of extremely hot plasma that can persist for millions of years and contribute to what astronomers call the hot ionized medium or coronal gas. This coronal component extends far above the galactic disk, forming a hot halo that reaches altitudes of several thousand parsecs and connects the interstellar medium of our galaxy to the broader intergalactic environment. The energy driving these extreme temperatures comes not only from individual supernova explosions, but also from the collective effects of stellar winds from massive stars, which create ongoing sources of heating that maintain the hot phase even between supernova events. The multiple phases of the interstellar medium exist in a state of dynamic equilibrium, with matter constantly cycling between phases as cooling processes condense hot gas into warm and cold components, while heating mechanisms driven by stellar energy injection work to ionize and heat cooler material. This phase structure creates a complex network of interfaces where different temperature regimes meet, leading to instabilities and mixing processes that transport energy and momentum across vast regions of the galaxy. Dust grains suspended throughout all phases of the interstellar medium play crucial roles in this ecosystem by providing surfaces where molecular hydrogen can form, by absorbing and re-emitting stellar radiation, and by serving as condensation nuclei that facilitate the transition from gas to solid matter. These microscopic particles, typically only a fraction of a micrometer in size, are composed primarily of silicate minerals and carbon compounds that condense in the atmospheres of dying stars and are subsequently dispersed throughout the galaxy by stellar winds and supernova explosions. The dust absorbs ultraviolet and visible light from stars and re-radiates this energy in the infrared, creating a component of the galactic radiation field that influences heating and cooling rates throughout the interstellar medium and affects the physical conditions in star-forming regions. The recycling of matter through stellar evolution processes connects all phases of the interstellar medium to the ongoing process of galactic chemical evolution, as massive stars synthesize heavy elements in their cores and disperse these products throughout interstellar space when they explode, gradually enriching the gas from which future generations of stars will form. This stellar recycling process operates on timescales of hundreds of millions of years, slowly transforming the chemical composition of the entire galaxy and creating the conditions necessary for the formation of planetary systems containing the heavy elements required for rocky planets and complex chemistry that can eventually lead to the development of life. Surrounding you right now, filling every cubic centimeter of space with perfect uniformity, is the oldest light in the universe, a faint afterglow from an epoch when the cosmos was only 320,000 years old and glowing like the surface of a star. This cosmic microwave background radiation maintains a nearly constant temperature of 2.725 degrees above absolute zero everywhere you look, creating a thermal bath that has been cooling steadily for over 13.8 billion years, as the expansion of space has stretched these ancient photons from their original visible wavelengths to the microwave frequencies we detect today. The cosmic microwave background represents a snapshot of the universe at the moment it transitioned from an opaque plasma filled with free electrons and protons to a transparent medium of neutral hydrogen atoms, a phase change that occurred when temperatures dropped sufficiently for electrons to bind with protons and form stable atoms for the first time in cosmic history. Before this recombination epoch, photons could not travel far before colliding with free electrons, keeping the universe in a state similar to the interior of a star where light constantly scatters and cannot escape. But once neutral atoms formed, photons were suddenly free to travel across cosmic distances without interference, flooding the universe with the thermal radiation that had been trapped since the Big Bang. The European Space Agency's Planck satellite, operating between 2009 and 2010, mapped this background radiation with unprecedented precision, detecting temperature variations as small as 1 part in 100,000 and revealing the intricate pattern of density fluctuations that existed in the primordial universe. These tiny temperature differences, invisible to less sensitive instruments, trace regions where matter was slightly denser or less dense than the cosmic average, creating the seeds from which all future cosmic structure would grow through gravitational amplification over billions of years of evolution. The Planck observation showed that these primordial fluctuations follow specific statistical patterns that provide detailed information about the fundamental properties of the universe, including its age, composition, and the physical processes that operated during its earliest moments. By analysing the sizes and amplitudes of temperature variations across different angular scales, cosmologists can determine that the universe is 13.799 billion years old, consists of 68.3% dark energy, 26.8% dark matter, and only 4.9% ordinary matter, while also measuring the rate of cosmic expansion and the curvature of space with extraordinary precision. Perhaps most remarkably, Planck detected polarization patterns in the cosmic microwave background that provide evidence for gravitational waves generated during cosmic inflation. The brief period of accelerated expansion that occurred in the first fraction of a second after the Big Bang. The polarization signals, caused by gravitational waves stretching and compressing the fabric of space-time itself, create distinctive spiral patterns in the cosmic microwave background that can be distinguished from other sources of polarization through careful statistical analysis. The detection of these primordial gravitational wave signatures would confirm that the universe underwent inflation and provide direct evidence for quantum fluctuations in spacetime geometry during the earliest moments of cosmic history, when the entire observable universe was smaller than a proton and subject to quantum mechanical uncertainty principles. The temperature fluctuations mapped by Planck serve as the cosmic DNA from which all current structure descended, with each hotspot marking a region destined to become a galaxy cluster, and each cold spot indicating a future cosmic void where matter would be scarce. Computer simulations that begin with the Planck initial conditions and evolve them forward through 13.8 billion years of gravitational growth successfully reproduce the cosmic web structure observed today, confirming that the tiny variations detected in the cosmic microwave background were indeed the seeds of galaxies, stars, and ultimately the complex structures that make life possible. The cosmic microwave background also provides the ultimate reference frame for measuring motion through space, as our movement through this thermal bath creates a dipole anisotropy pattern where the radiation appears slightly hotter in the direction we are moving and slightly cooler in the opposite direction. This measurement reveals that our solar system moves at 371 kilometers per second relative to the cosmic microwave background rest frame, carried along by the motion of our galaxy through the cosmic web and providing a way to measure our absolute velocity through the universe rather than just our motion relative to nearby objects. The uniformity of the cosmic microwave background across opposite sides of the sky demonstrates that regions now separated by distances much larger than light could have travelled since the Big Bang were once in thermal equilibrium, providing strong evidence for cosmic inflation as the mechanism that established this remarkable large-scale coherence in the early universe. Racing through the space around you at this very moment are some of the most energetic particles ever detected, cosmic rays with individual energies that can exceed the total kinetic energy of a baseball thrown by a major league pitcher, despite being concentrated in single atomic nuclei smaller than any virus. These cosmic messengers arrive at Earth from two distinct populations, galactic cosmic rays that have been accelerated within our own Milky Way galaxy to energies below about 1,000,000 billion electron volts, and ultra-high energy extragalactic cosmic rays that originate in distant galaxies and carry energies exceeding 100 million billion electron volts, placing them among the most extreme phenomena in the observable universe. The Pierre Auger Observatory in Argentina, the largest cosmic ray detector ever built, has recorded individual particles with energies approaching 100 billion electron volts, which corresponds to the kinetic energy of a tennis ball travelling at 100 kilometers per hour concentrated in a single proton or atomic nucleus. These ultra-high energy particles are so rare that they strike each square kilometre of Earth's surface only about once per century, requiring detection arrays that span thousands of square kilometres to collect sufficient data for statistical analysis, but their extreme energies provide unique insights into the most violent acceleration processes operating anywhere in the cosmos. The transition between galactic and extragalactic cosmic ray populations occurs at an energy known as the ankle, around a few billion electron volts, where the cosmic ray energy spectrum changes slope in a way that indicates a shift from sources within our galaxy to sources in distant galaxies and galaxy clusters. Below this transition energy, cosmic rays are trapped within the Milky Way by our galaxy's magnetic field, which deflects their paths and prevents them from escaping into intergalactic space, causing them to wander through the galactic environment for millions of years before finally reaching Earth, from seemingly random directions that bear no relation to their original sources. The galactic magnetic field creates invisible highways that channel cosmic ray propagation, with particles following complex spiral trajectories around magnetic field lines, while gradually diffusing across field line boundaries through interactions with magnetic turbulence and plasma waves. This magnetic confinement process means that cosmic rays with energies below the ankle have had ample time to interact with the interstellar medium during their long journeys through the galaxy, creating cascades of secondary particles that include neutrons, pions, muons, neutrinos, and gamma rays through nuclear collisions with hydrogen and helium nuclei in interstellar space. These secondary particle interactions represent one of the primary mechanisms for cosmic ray energy loss and also serve as sources of other forms of radiation that fill the space between stars, including the neutrino emissions detected by IceCube and the diffuse gamma ray background observed by the Fermi Space Telescope. At the highest energies, where cosmic rays become too energetic to be confined by galactic magnetic fields, particles can travel in nearly straight lines across intergalactic distances, making them direct messengers from their sources in distant active galactic nuclei, gamma ray bursts, or other extreme astrophysical environments. However, even these ultra-high energy particles face energy loss mechanisms during their extragalactic journeys, particularly interactions with the cosmic microwave background radiation that fills all of space and provides a target for nuclear interactions at sufficiently high energies. The Greisen-Zatsepin-Kuzmin cutoff, predicted in the 1960s, sets a theoretical maximum energy for cosmic ray protons propagating across cosmological distances because particles with energies exceeding about 50 billion electron volts will interact with cosmic microwave background photons and lose energy through photopion production, effectively limiting the distances from which the most energetic cosmic rays can reach Earth. Observations by the Pierre Auger Observatory have confirmed the existence of this energy cutoff, providing evidence for cosmic microwave background interactions and constraining the distances to ultra-high energy cosmic ray sources to within about 100 million light-years of Earth. The composition of cosmic rays changes with energy, with low-energy galactic cosmic rays consisting primarily of hydrogen nuclei mixed with heavier elements like helium, carbon and iron, while ultra-high energy extragalactic cosmic rays appear to be predominantly heavy nuclei that have been stripped of all their electrons during the acceleration process. This composition evolution reflects different acceleration mechanisms operating in galactic versus extragalactic sources, with supernova shockwaves and pulsar magnetospheres providing the primary acceleration for galactic cosmic rays, while relativistic jets from supermassive black holes and other exotic phenomena generate the ultra-high energy extragalactic population. The study of cosmic ray propagation through magnetic fields also provides information about the structure and strength of magnetic fields throughout the galaxy and in intergalactic space, as particle arrival directions and energy spectra preserve signatures of the magnetic environments through which they have travelled during their journeys from source to detector. Every point in space around you bathes in a sea of electromagnetic radiation spanning the entire spectrum from the longest radio waves to the most energetic gamma rays, creating an ambient radiation field that carries the accumulated light from every star that has ever shone, and every energetic process that has ever occurred throughout cosmic history. This interstellar radiation field represents the combined electromagnetic output of 13.8 billion years of stellar evolution, supernova explosions, black hole activity, and cosmic ray interactions, all mixed together into a diffuse background that fills every cubic centimetre of the galaxy, with photons carrying energies from the infrared through the ultraviolet and beyond. The optical component of this radiation bath consists primarily of starlight that has been emitted by the hundreds of billions of stars in our galaxy and scattered by interstellar dust, creating a faint glow that would be detectable throughout the galactic disk, even in regions far from individual stellar sources. Much of this starlight gets absorbed by microscopic dust grains composed of silicate minerals and carbon compounds that condense in the atmospheres of dying stars and become distributed throughout interstellar space, where they intercept stellar ultraviolet and visible light and re-radiate this energy at longer infrared wavelengths, corresponding to dust temperatures of 10 to 100 degrees Kelvin. This dust emission creates a substantial infrared background that dominates the electromagnetic energy density in many regions of the galaxy, particularly in the dense molecular clouds where new stars form and where dust concentrations can become so high that they completely block visible light while glowing brightly in far infrared wavelengths. This radio component of the interstellar radiation field originates primarily from synchrotron emission, produced when cosmic ray electrons spiral around magnetic field lines at relativistic velocities, creating a diffuse radio glow that traces the galactic magnetic field structure and reveals the distribution of high-energy particles throughout the galaxy. This synchrotron radiation extends across a broad range of radio frequencies from a few megahertz to several gigahertz, with the spectral characteristics providing information about both the cosmic ray electron energy spectrum and the strength of magnetic fields in different regions of interstellar space. At the highest energies, gamma-ray photons fill the interstellar radiation field through several production mechanisms, including cosmic ray interactions with interstellar gas that produce neutral pions, which decay into gamma-ray pairs, inverse Compton scattering, where cosmic ray electrons boost low-energy photons to gamma-ray energies, and bremsstrahlung radiation emitted when cosmic ray electrons are decelerated by electromagnetic interactions with atomic nuclei. The gamma-ray background also includes contributions from distant unresolved sources like active galactic nuclei and gamma-ray bursts, creating a truly universal radiation field that that connects our local galactic environment to energetic phenomena occurring throughout the observable universe. The energy density of the interstellar radiation field varies significantly with location within the galaxy, reaching maximum values near the galactic center, where stellar densities are highest, and dropping to minimum values in the outer galactic halo, where stars become scarce and dust concentrations diminish. Near the solar system, the total energy density of the interstellar radiation field equals roughly 1 electron volt per cubic centimeter, which is comparable to the energy density of cosmic ray particles in interstellar magnetic fields, making an electromagnetic radiation a significant component of the total energy budget that determines the physical conditions and evolutionary processes operating in the local interstellar medium. This radiation field plays crucial roles in heating interstellar gas through photoelectric emission from dust grains and photoionization of atoms, while also providing the energy source for photodissociation processes that break apart molecules and regulate the chemical composition of interstellar clouds. The intensity and spectral characteristics of the interstellar radiation field also determine the visibility of astronomical objects at different wavelengths, with dust absorption creating wavelength-dependent extinction that makes distant stars appear redder and fainter than they would in the absence of interstellar matter. Perhaps most remarkably, this electromagnetic bath carries information about cosmic history encoded in photons that have been travelling through space for billions of years, with some radio waves originating from processes that occurred when the universe was only a fraction of its current age, and some gamma rays produced by cosmic ray interactions involving particles that were accelerated in supernova explosions that occurred before our solar system formed. The cosmic microwave background contributes a uniform component to this radiation field at millimeter wavelengths, while the accumulated light from all galaxies beyond our own creates an extragalactic background that extends from radio through gamma-ray energies and represents the integrated electromagnetic output of the entire observable universe over cosmic time. Even in regions of space completely devoid of matter, radiation, and any detectable particles, the quantum vacuum seethes with invisible activity as virtual particles spontaneously appear and disappear in accordance with Heisenberg's uncertainty principle, which allows energy and matter to be borrowed from the fabric of space-time itself for incredibly brief moments before being annihilated and returned to the void. This quantum foam, as physicists call it, represents the irreducible minimum level of activity that can exist in any region of space, arising from the fundamental quantum fields that fill the universe and create fluctuations in energy density even when no real particles are present. Quantum field theory describes reality not as empty space punctuated by particles, but as a collection of fields permeating all of spacetime, with particles representing localized excitations in these fields, while the vacuum state corresponds to the lowest possible energy configuration where virtual particle pairs continuously pop into existence and annihilate each other on timescales so short that they cannot be directly observed but nevertheless produce measurable physical effects. The zero-point energy of these quantum fields represents an enormous energy density that, if it could be harnessed, would dwarf any conventional energy source, but this vacuum energy remains largely inaccessible because it exists in the ground state of the quantum system and cannot be extracted without violating conservation laws. However, the reality of vacuum fluctuations can be demonstrated through the Casimir effect discovered in 1948, where two uncharged metal plates placed extremely close together in empty space experience a tiny attractive force because the quantum vacuum between the plates can support fewer virtual particle modes than the vacuum outside the plates, creating a pressure difference that pushes the plates together. This effect has been measured with extraordinary precision using atomic force microscopes and other sensitive instruments, confirming that the quantum vacuum possesses real physical properties that can influence macroscopic objects and providing direct experimental evidence for the existence of zero-point energy fluctuations predicted by quantum field theory. The implications of vacuum fluctuations extend far beyond laboratory physics to some of the most extreme environments in the universe, particularly near black hole event horizons where the intense gravitational fields can convert virtual particle pairs into real particles through a process known as Hawking radiation. When virtual particle pairs form near a black hole's event horizon, the intense gravitational field can separate the pair before they annihilate, with one particle falling into the black hole while the other escapes to infinity, effectively allowing the black hole to convert vacuum energy into real particles and radiation, while slowly evaporating through this quantum process. This mechanism demonstrates that even the most extreme gravitational environments cannot eliminate quantum vacuum fluctuations, but instead can amplify them into observable phenomena that reveal the deep connections between quantum mechanics, general relativity, and thermodynamics. Perhaps most intriguingly, some theoretical physicists have proposed that dark energy, the mysterious force causing the accelerated expansion of the universe, might be related to the energy density of quantum vacuum fluctuations. Though this connection faces the enormous challenge that naive calculations of vacuum energy density exceed the observed dark energy density by factors of 10 or 20, making it one of the largest discrepancies between theory and observation in all of physics. This vacuum catastrophe, as it is known, suggests either that our understanding of quantum field theory in curved spacetime is fundamentally incomplete, or that some unknown mechanism suppresses most of the vacuum energy contribution to cosmic expansion, leaving only a tiny residual effect that manifests as dark energy. Alternative approaches to this problem include theories where the vacuum energy density adjusts itself dynamically to minimize the total energy of the universe, or models where quantum fluctuations contribute to dark energy only indirectly through their influence on other fields or fundamental constants. Recent advances in quantum field theory in curved spacetime have also revealed that the definition of the vacuum state itself becomes ambiguous in the presence of strong gravitational fields or accelerated motion, with different observers potentially defining different vacuum states that contain different amounts of energy and particle content. The Unruh effect predicted by quantum field theory suggests that an accelerated observer will detect thermal radiation in what an unaccelerated observer considers empty vacuum, while the Hawking effect shows that black holes possess temperature and entropy that arise entirely from quantum properties of spacetime geometry rather than classical thermodynamics. These discoveries have led to profound questions about the fundamental nature of space, time, energy, and information, with some physicists proposing that spacetime itself might emerge from more fundamental quantum mechanical structures rather than being a basic feature of reality, and others suggesting that the apparent emptiness of space conceals vast amounts of quantum information that determine the properties of particles and forces through holographic principles that connect the physics of surfaces to the physics of volumes. The space around you is not the empty stage upon which cosmic events unfold, but rather a dynamic medium that curves, stretches, and vibrates in response to every massive object and energetic process throughout the universe, creating a geometry that itself carries information about the gravitational history of everything that has ever existed. Einstein's general relativity revealed that what we experience as gravity is actually the curvature of space-time itself, with massive objects like stars and planets creating depressions in the fabric of reality that guide the motion of other objects along paths we interpret as gravitational attraction. While the most violent events in the cosmos send ripples through this curved geometry at the speed of light, carrying energy and information across billions of light years. These gravitational waves, first detected directly by the LIGO and Virgo observatories in 2015, represent oscillations in space-time itself, with amplitudes so small that they stretch and compress distances by less than 1/10,000th the width of a proton, yet they carry more energy than all the stars in the observable universe emit in electromagnetic radiation, demonstrating the incredible sensitivity required to detect these fundamental disturbances in the structure of reality. The detection of gravitational waves opened an entirely new window for observing the universe, revealing phenomena that remain completely invisible to electromagnetic telescopes, including the final moments of black hole mergers where two regions of curved spacetime spiral into each other at velocities approaching the speed of light before combining into a single, more massive black hole that rings like a struck bell as it settles into its final configuration. The spacetime around rotating massive objects exhibits even more complex behavior through frame-dragging effects, where the rotation of matter literally twists the geometry of space and time, causing nearby objects to be dragged along with the rotation regardless of any forces acting upon them. This gravitomagnetic effect has been measured around Earth using precision satellite experiments that detected tiny changes in satellite orbits caused by our planet's rotation dragging space-time along, like honey stirred by a spinning spoon, confirming Einstein's predictions about the dynamic nature of space-time geometry. Even more remarkably, gravitational waves can create permanent changes in spacetime geometry through gravitational memory effects, where the passage of intense gravitational radiation leaves lasting deformations that persist long after the waves themselves have passed, creating a form of cosmic memory embedded in the curvature of space itself. These memory effects mean that spacetime preserves information about every gravitational wave that has ever passed through a given region, potentially allowing future ultra-sensitive detectors to read the gravitational history of the universe directly from measurements of spacetime curvature rather than relying on electromagnetic signals that can be absorbed, scattered or redshifted during their journey across cosmic distances. The information content of spacetime geometry extends beyond gravitational wave memory to include the complete gravitational field configuration that determines how matter and energy will behave in every region of the universe, making spacetime itself a kind of cosmic database that stores the positions, masses, and motions of every object while also encoding the boundary conditions that govern future evolution. This geometric encoding of information becomes particularly important near black holes, where the intense curvature of spacetime can store enormous amounts of information on the event horizon surface through holographic principles that relate the information content of any volume to the area of its boundary, rather than its internal volume. The study of gravitational waves has also revealed that spacetime possesses a rich spectrum of oscillatory modes that extend far beyond the merger events detected by current instruments, including continuous gravitational wave emission from rapidly rotating neutron stars with asymmetric mass distributions, stochastic gravitational wave backgrounds created by the superposition of countless unresolved sources throughout cosmic history, and potentially primordial gravitational waves generated during cosmic inflation that would carry information about the universe when it was less than a second old. Future gravitational wave detectors operating in space, including the planned LISA mission, will be sensitive to much lower frequency gravitational waves than ground-based instruments can detect, opening access to different classes of sources including supermassive black hole mergers, white dwarf binary systems throughout our galaxy, and the continuous gravitational wave background created by the cosmic web structure formation process. The recognition that spacetime itself serves as both medium and message in gravitational wave astronomy has led to new theoretical insights about the fundamental nature of space-time and information, with some physicists proposing that spacetime geometry might emerge from more fundamental quantum information processing principles rather than being a basic feature of reality, while others explore whether gravitational effects might provide new mechanisms for storing and manipulating information that could eventually be exploited for technological applications ranging from ultra-precise navigation to quantum computing architectures that utilize the geometric properties of curved spacetime. At the deepest level, the space around you may not be the continuous smooth medium that it appears to be, but rather a discrete structure built from fundamental units of information encoded at the Planck scale, where distances become so small that the very concepts of space and time begin to break down and reveal their true nature as emergent properties arising from more fundamental quantum mechanical processes. The holographic principle, one of the most revolutionary ideas in modern physics, suggests that all the information contained within any volume of space can be encoded on its two-dimensional boundary surface, with each unit of surface area at the Planck scale capable of storing exactly one bit of information, making the interior volume essentially redundant and implying that what we experience as three-dimensional space might actually be a holographic projection from information stored on distant surfaces. This principle emerged from studies of black hole thermodynamics, where physicists discovered that the entropy of a black hole scales with the area of its event horizon rather than its volume, leading to the startling realization that the maximum information content of any region is determined by its surface area rather than its internal capacity, fundamentally challenging our intuitions about how information and space are relate. The Planck length, approximately 10⁻35 meters, represents the scale at which quantum mechanical uncertainties in the measurement of distance become comparable to the gravitational effects of the measuring apparatus itself, creating a fundamental limit to the precision with which spacetime can be probed and suggesting that space itself might possess a discrete granular structure at this scale, rather than being infinitely divisible. Loop quantum gravity, one of the leading approaches to quantum gravity, proposes that spacetime is indeed discrete at the Planck scale, consisting of fundamental loops of quantized geometry that weave together to create the fabric of reality, with each loop carrying a quantum of area or volume that cannot be subdivided further. making space itself atomic in the same sense that matter is composed of indivisible atoms. In this picture, the smooth spacetime of Einstein's general relativity emerges as a statistical average over vast numbers of these discrete geometric elements, similar to how the continuous flow of water emerges from the statistical behavior of countless individual molecules that are themselves discrete and granular. Recent theoretical developments have suggested that spacetime might emerge entirely from quantum entanglement, the mysterious quantum mechanical correlation that can instantaneously connect particles across arbitrary distances with the geometric properties of space arising naturally when quantum information becomes entangled in specific patterns that encode distance and connectivity relationships. This emergence scenario implies that information, rather than space and time, represents the most fundamental level of reality, with space-time geometry serving as an effective description that captures the large-scale statistical properties of underlying quantum information processing systems. The relationship between information and geometry becomes particularly striking in the context of quantum error correction, where physicists have discovered that the same mathematical structures used to protect quantum information from corruption can also describe the emergence of curved spacetime from quantum entanglement networks, suggesting deep connections between information theory, quantum mechanics, and gravity. These insights have led to speculation that the universe itself might function as a vast quantum computer, with physical processes representing information processing operations that manipulate the fundamental quantum states from which spacetime emerges, making every particle interaction and field fluctuation part of a cosmic computation that continuously updates the geometry of reality. The discreteness of spacetime at the Planck scale also implies that there are fundamental limits to the amount of information that can be stored or processed in any finite region, with these limits determined by the holographic bound that restricts information content to 1 bit per unit of Planck area, potentially explaining why physics appears to be governed by finite calculable numbers, rather than infinite quantities that would make the universe incomputable. Some theoretical physicists have proposed that these information-theoretic limits might explain the values of fundamental constants and the apparent fine-tuning of physical laws for the existence of complex structures, suggesting that universes capable of storing and processing information efficiently would naturally evolve physical laws that permit the emergence of galaxies, stars, planets, and life. The holographic principle also provides new perspectives on the nature of consciousness and observation, with some theorists speculating that consciousness might represent a particular type of information processing that occurs when quantum systems become sufficiently complex and interconnected, potentially making awareness itself an emergent property of information processing networks rather than a fundamental feature that requires explanation in terms of classical physics. These ideas remain highly speculative and contentious, but they illustrate how the discovery that space itself might be constructed from information has profound implications that extend far beyond physics into questions about the nature of reality, consciousness, and the ultimate structure of existence itself. The invisible architecture of the cosmos that fills the space between stars plays an essential role in creating and sustaining the conditions necessary for life, with dark matter scaffolding providing the gravitational framework that enabled galaxies to form quickly enough after the Big Bang to begin the stellar nucleosynthesis processes that would eventually produce the carbon, oxygen, nitrogen, and other heavy elements required for complex chemistry and biological processes. Without dark matter providing this cosmic infrastructure, the universe would have remained a nearly uniform soup of hydrogen and helium for billions of additional years, preventing the formation of the first stars and delaying or possibly preventing entirely the chemical evolution that makes planets and life possible. The cosmic web serves as a vast circulatory system that continuously delivers fresh gas to galaxies along filamentary highways, sustaining star formation over billions of years and ensuring that galaxies can continue producing new generations of stars enriched with heavy elements synthesized in the cores of previous stellar generations. This ongoing gas supply proves crucial for biological evolution because life requires not only the presence of heavy elements, but their continuous cycling through stellar birth and death processes that create planetary systems with the chemical diversity and energy sources necessary for complex organic chemistry. The dispersal of heavy elements throughout the intergalactic medium occurs through supernova explosions and stellar winds that inject carbon, nitrogen, oxygen, silicon, iron, and dozens of other elements into the cosmic web, where they become incorporated into future generations of stars and planets across vast cosmic distances. This chemical enrichment process means that every atom in your body except hydrogen was forged in stellar cores and transported through the cosmic web before eventually becoming part of Earth, connecting your biological existence directly to processes occurring throughout the galaxy and demonstrating that life represents a cosmic rather than purely planetary phenomenon. The galactic magnetic fields that thread through interstellar space provide crucial protection for planetary systems by deflecting high-energy cosmic ray particles that could otherwise sterilize planetary surfaces and destroy the atmospheric chemistry necessary for life. Without this magnetic shielding, planets would be bombarded by cosmic radiation intense enough to strip away atmospheres and break apart the complex organic molecules that serve as the building blocks of living systems, making the invisible magnetic infrastructure of the galaxy an essential component of habitability. Paradoxically, cosmic rays also appear to play important beneficial roles in biological evolution by providing a source of genetic mutations that drive evolutionary adaptation, and by triggering atmospheric chemistry processes that can influence climate and the formation of organic compounds in planetary atmospheres. Studies of Earth's geological record suggest that cosmic ray flux variations correlated with our solar system's motion through different regions of the galactic magnetic field may have influenced major evolutionary transitions, climate changes, and extinction events throughout biological history. The cosmic web also determines which regions of the universe are most likely to develop conditions suitable for life by concentrating matter and energy into filamentary structures where star formation rates remain high enough to maintain chemical evolution while avoiding the extreme radiation environments found in galaxy cluster cores where tidal forces and active galactic nuclei create hostile conditions for planet formation and atmospheric retention. Recent research has revealed that the majority of potentially habitable planets may exist in cosmic web filaments rather than in massive galaxy clusters, with the gentle gravitational environment and moderate star formation rates in these regions providing optimal conditions for long-term planetary stability and atmospheric evolution. The timing of cosmic structure formation also proves crucial for life, with computer simulations showing that if dark matter had different properties, or if the cosmic web had formed significantly earlier or later in cosmic history, the resulting universe might have been either too violent or too quiescent to support the complex sequence of stellar evolution, planetary formation, and chemical enrichment that biological systems require. Even the expansion rate of the universe influences habitability by determining how long galaxies can continue forming. Stars and maintaining the energy sources necessary for planetary geophysics and atmospheric dynamics that sustain habitable climates over geological timescales. The recognition that life depends on cosmic-scale processes has led to the emerging field of astrobiology to consider habitability from a cosmic perspective, examining how galactic environment, cosmic ray exposure, heavy element abundance, and magnetic field protection combine to create galactic habitable zones where conditions favour the emergence and evolution of complex biological systems. This cosmic context reveals that the seemingly empty space surrounding every star and planet actually contains the invisible infrastructure that makes life possible, from the dark matter scaffolding that enabled galaxy formation to the magnetic highways that protect planetary atmospheres, demonstrating that biological evolution represents not an isolated planetary process, but rather the natural outcome of cosmic evolution operating on the largest scales through the hidden architecture of the universe. The next few decades will witness an unprecedented revolution in our ability to study the hidden universe as new generations of telescopes, detectors, and observational techniques reveal invisible structures and phenomena that remain completely inaccessible to current instruments, fundamentally transforming our understanding of cosmic architecture and the forces that shape reality on the largest scales. The James Webb Space Telescope represents just the beginning of this observational revolution, with planned successors like the Nancy Grace Roman Space Telescope and the Extremely Large Telescope, promising even greater sensitivity to the infrared radiation that traces dark matter structure, while specialized missions like Euclid and the Vera Rubin Observatory will map billions of galaxies to create three-dimensional maps of dark matter distribution across cosmic history with unprecedented precision. Ground-based dark matter detection experiments are rapidly approaching the sensitivity levels required to directly observe individual dark matter particle interactions with detectors like the The Lux Zeppelin experiment, using tons of liquid xenon buried deep underground to shield against cosmic ray background and detect the tiny energy deposits that would result from dark matter particles colliding with atomic nuclei. These experiments operate at the intersection of particle physics and cosmology, seeking to identify the fundamental nature of the substance that comprises 85% of all matter in the universe and provides the gravitational scaffolding for cosmic structure formation, with potential discoveries that would revolutionize both our understanding of particle physics and our models of cosmic evolution. The expansion of gravitational wave astronomy promises to reveal entirely new aspects of the hidden universe as more sensitive detectors come online, including the space-based LISA mission that will detect gravitational waves from supermassive black hole mergers across cosmic distances and potentially primordial gravitational waves generated during cosmic inflation that carry information about the universe when it was less than a second old. These gravitational wave observations will provide direct measurements of space-time curvature and dynamics that complement electromagnetic observations, creating a new form of astronomy that can study phenomena invisible to conventional telescopes and reveal the most violent events in cosmic history through their gravitational signatures rather than their electromagnetic emissions. The multi-messenger astronomy revolution, which combines gravitational waves, neutrinos, cosmic rays, and electromagnetic radiation in coordinated observations, is transforming our ability to study cosmic phenomena by providing multiple independent channels for observing the same events and revealing different aspects of the physics operating in extreme astrophysical environments. Future neutrino observatories, including the planned IceCube Gen 2 detector with 10 times the sensitivity of current instruments and massive underwater neutrino telescopes in the Mediterranean and Pacific, will detect neutrinos from individual supernova explosions throughout our galactic neighborhood while also studying the diffuse neutrino background created by all cosmic ray interactions throughout the universe. The mystery of dark energy, which drives the accelerating expansion of the universe and comprises roughly 68% of the cosmic energy budget, represents perhaps the greatest challenge for future observational cosmology, with planned surveys like the Dark Energy Survey and the Large Synoptic Survey telescope designed to measure cosmic expansion history and structure growth with sufficient precision to distinguish between different theoretical models for dark energy behavior. These observations will determine whether dark energy represents a cosmological constant with fixed energy density or a dynamic field that changes over cosmic time, with implications for the ultimate fate of the universe and the fundamental nature of space-time itself. Advanced computer simulations incorporating dark matter, dark energy, magnetic fields, and cosmic ray propagation are reaching unprecedented levels of realism, allowing scientists to predict the detailed structure of the cosmic web and test theoretical models against observations, while also exploring how different assumptions about dark matter properties or dark energy evolution would affect cosmic structure formation. Machine learning techniques are revolutionizing the analysis of astronomical data by automatically identifying patterns in observations that would be impossible to detect through traditional analysis methods, potentially revealing new classes of cosmic phenomena or subtle signatures of dark matter interactions that have been overlooked in previous surveys. The development of quantum sensors and atomic interferometry techniques promises to enable new types of dark matter searches and gravitational wave detectors with sensitivities that exceed current instruments by many orders of magnitude, potentially opening entirely new observational windows that could reveal aspects of the hidden universe that remain completely unknown. Future space missions will also explore the possibility that dark matter or dark energy interactions produce observable signatures in planetary motion, asteroid trajectories, or satellite orbits, using the solar system itself as a laboratory for testing theories about invisible cosmic components. The convergence of these diverse observational and theoretical approaches suggests that the next century may witness discoveries about the hidden universe that are as revolutionary as the original detection of cosmic expansion or the discovery of dark matter, potentially revealing new physics beyond the standard model of particle physics and fundamentally altering our understanding of space, time, matter, and energy. As you rest quietly in this moment, every atom that forms your body carries within it a cosmic history that spans billions of years of travel through the invisible architecture of the universe, from its birth in stellar cores to its journey along cosmic web filaments through interstellar magnetic highways and finally to its temporary residence in the complex chemistry of life before it continues its eternal cosmic odyssey. The carbon atoms in your muscles and bones were forged in the nuclear furnaces of massive stars that exploded as supernovas, dispersing their contents into the cosmic web, where these atoms spent eons drifting through hot intergalactic plasma, cold molecular clouds, and the gravitational embrace of dark matter halos before eventually condensing into the solar system and becoming part of Earth's biosphere. Your existence represents a temporary configuration of cosmic matter that has been continuously cycling through the galaxy for billions of years, connecting you directly to processes occurring throughout the cosmic web and making you literally part of the living universe rather than a separate observer studying it from the outside. At this very moment, your body participates in an ongoing exchange with the interstellar medium as cosmic ray particles penetrate your cells, neutrinos from distant galaxies pass through your neurons, and the atoms you breathe were once scattered across vast distances through the galactic magnetic field before being swept up by our solar system's motion through space. The cosmic rays that continuously bombard Earth influence our planet's climate through complex interactions with the atmosphere that affect cloud formation, precipitation patterns, and atmospheric chemistry, creating subtle connections between galactic magnetic field variations and terrestrial weather systems that link local environmental conditions to our solar system's position within the cosmic web. These cosmic influences extend beyond climate to potentially affect biological evolution itself, with fluctuations in cosmic ray intensity correlated with major evolutionary transitions in Earth's history, suggesting that the invisible forces shaping galactic structure may also influence the development of life and consciousness across cosmic timescales. Even more remarkably, your body is continuously permeated by neutrinos created during the Big Bang itself, primordial particles that have been travelling through space for over 13 billion years and now pass through you at a rate of several hundred million per square centimetre every second, carrying within them information about the universe's earliest moments and connecting your present existence to the cosmic creation event. This continuous bombardment by ancient neutrinos means that you exist within the afterglow of cosmic creation, literally bathed in remnant particles from the Big Bang that provide a direct physical link between your consciousness and the fundamental processes that brought the universe into existence. The development of human consciousness represents something truly extraordinary in cosmic evolution: the emergence of complex information processing systems capable of understanding and contemplating the very cosmic web from which they arose, making consciousness potentially the universe's mechanism for becoming self-aware and understanding its own structure and evolution. Through scientific observation and mathematical reasoning, human minds have discovered the invisible dark matter scaffolding, mapped the cosmic web filaments, detected gravitational waves from distant black hole mergers, and revealed the quantum foam that underlies space-time itself, effectively enabling the universe to study its own hidden architecture through biological neural networks that emerged from cosmic processes. This perspective suggests that consciousness may represent not an accidental byproduct of complex chemistry, but rather a natural outcome of cosmic evolution, arising when information processing becomes sophisticated enough to model and understand the very processes that created the information processes themselves. The atoms in your brain that enable conscious thought have journeyed across cosmic distances through dark matter, halos, along magnetic field lines, and through hot intergalactic plasma before becoming organized into neural networks capable of contemplating their own cosmic origins and the invisible forces that guided their assembly. Your thoughts about the hidden universe are themselves made possible by the cosmic web that delivered the heavy elements necessary for complex chemistry, the magnetic fields that protected Earth's atmosphere from cosmic ray sterilization, and the dark matter structures that enabled galaxies to form quickly enough to begin the stellar nucleosynthesis processes required for life. In this sense, human consciousness represents the cosmic web becoming aware of itself, with every scientific discovery about dark matter, dark energy, and cosmic structure representing the universe's growing self-knowledge, expressed through biological information processing systems that arose from the same cosmic processes they now study. The invisible architecture surrounding you is not separate from your existence, but rather the very foundation that makes consciousness possible, creating a profound unity between mind and cosmos that suggests the deepest questions about consciousness and cosmic structure may ultimately be the same question approached from different perspectives, with human awareness serving as the universe's method for understanding its own hidden nature. The silence between stars emerges not as emptiness, but as the foundation for a cosmic symphony, where dark matter, hot plasma, magnetic fields, quantum fluctuations, gravitational waves and neutrino streams weave together in an eternal dance that has orchestrated the universe's evolution for 13.8 billion years and will continue to shape reality for trillions of years to come. This dynamic, interconnected system operates on every scale, from quantum foam fluctuations at the Planck length to cosmic web filaments spanning billions of light years, with each component influencing all others through gravitational, electromagnetic, and quantum mechanical interactions that create feedback loops connecting the smallest and largest structures in existence. The apparently empty space that surrounds every star, planet, and galaxy serves as the stage upon which this cosmic choreography unfolds, providing the medium through which information, energy, and matter flow between distant regions and enabling the complex processes that give rise to galaxies, stars, planets, and ultimately consciousness itself. As the universe continues to expand and evolve, these invisible forces will guide future cosmic development through processes that extend far beyond human timescales, with dark energy driving accelerated expansion that gradually stretches cosmic web filaments until they become so tenuous that galaxy formation ceases and star formation rates decline across billions of years. The long-term fate of this cosmic dance depends critically on the nature of dark energy and whether it represents a cosmological constant that maintains fixed energy density as space expands, or a dynamic field that could strengthen, weaken, or even reverse sine over cosmic timescales, leading to dramatically different ultimate destinies for the universe. If dark energy remains constant, the cosmic web will gradually dissolve as accelerated expansion overcomes gravitational attraction on all but the smallest scales, eventually leaving behind isolated galaxy groups surrounded by vast regions of empty space where the cosmic microwave background has redshifted to undetectable wavelengths and the last stars slowly fade into darkness. Alternatively, if dark energy represents a dynamic field that could change behavior over cosmic time, the universe might experience cycles of expansion and contraction driven by variations in dark energy density, potentially leading to a cyclic cosmology where the current expansion phase reverses into contraction, causing the cosmic web to collapse and possibly triggering a new Big Bang that would restart cosmic evolution with different initial conditions. Even in scenarios leading to heat death, where cosmic expansion continues indefinitely and star formation eventually ceases, the invisible architecture of space will persist through quantum fluctuations, gravitational wave propagation, and neutrino interactions that maintain subtle activity long after all conventional energy sources have been exhausted. The black holes that represent the ultimate fate of massive stars will continue to evaporate through Hawking radiation over timescales, exceeding 10 to 67 years, slowly returning their mass energy to the quantum vacuum through processes that connect the smallest and largest scales of physics, while demonstrating that even the most extreme gravitational environments cannot eliminate the quantum activity that fills all space. Throughout these vast timescales, the fundamental forces and fields that create the hidden architecture of space will continue operating according to physical laws that appear to possess a mathematical beauty and elegance that suggests deep connections between consciousness, mathematics, and the structure of reality itself. The fact that human minds, which arose through cosmic evolution from the same processes that created galaxies and stars, can discover and appreciate the mathematical relationships governing dark matter, quantum fields, and space-time geometry hints at profound links between the structure of consciousness and the structure of the cosmos that may represent more than mere coincidence. This mathematical harmony extends from the simple inverse square law of gravitation that shapes cosmic web architecture to the complex quantum field equations that govern vacuum fluctuations, revealing patterns and symmetries that connect apparently disparate phenomena through underlying principles of extraordinary mathematical elegance. The beauty inherent in these cosmic relationships suggests that the invisible universe operates according to principles that transcend mere mechanical causation, exhibiting forms of organization and complexity that inspire wonder and contemplation in conscious observers who represent the universe's own attempt to understand its hidden nature. As you rest in the apparent stillness of night, surrounded by this invisible cosmic architecture, you participate in the eternal dance of matter, energy, space and time that connects quantum fluctuations to the galactic clusters, primordial neutrinos to gravitational waves, and human consciousness to the deepest structures of reality. The silence between stars speaks not of emptiness, but of fullness, not of absence, but of presence, not of void, but of the infinite richness of a universe where every cubic centimetre of space teems with invisible activity that makes existence possible and beautiful beyond human comprehension. Thank you for drifting with me through the hidden fullness of what only appears empty. If this quiet exploration brought you a moment of wonder, a gentle like or subscribe would mean the world to me, helping these cosmic stories find their way to other wandering minds who seek peace in the vastness above. I'd love to know where you are listening tonight and what invisible mysteries you'd like us to explore together next time. Until then, may you rest knowing that the silence surrounding you pulses with ancient light, quantum whispers, and the gentle dance of forces that connect your breath to the farthest reaches of space. Sleep well under the hidden cosmos.